There were several overall goals of this lab. First, we were to observe the interactions of an aluminum tube and a magnet system and collect data on the time it takes for the magnet to travel through the tube. Next, we created a computational model of the same system, modeling the tube as a series of rings and the magnet as a dipole. And finally, we compared the computational and experimental models. There were several fundamental principles being used in this lab. First, we had to calculate the magnetic field using this general equation. We also had to use Faraday's law and Biot-Savart law. We had to be able to calculate net force, incorporating gravitational force and magnetic force. And we also incorporated Newton's second and third laws. For the experiment, the first thing we did was find the north pole of the bar magnet using the Teslameter app. We found this by orienting the magnet so the x value of the field was positive, and then we knew that the end closest to the app was the north pole. As a checkpoint, we knew we must use a non-ferrous metal as the tube because ferrous metals are generally magnetic. The results of the experiment showed that the average time it took the magnet to fall through the tube was 2.02 seconds. This is slower than a magnet falling through free space. Next, a computational model of the same system was created. First, the geometry of the tube was edited to match the dimensions of the tube used in the experiment. Then, the mass of the magnet and the mu value was adjusted to match the magnet used in the experiment as well. Next, two functions were created. One was created to calculate the magnetic field of the bar magnet, while the other was created to calculate the change in magnetic flux over time through the tube. Next, the net force, which included magnetic and gravitational forces on the magnet, was calculated. The magnetic force was calculated using the Biot-Savart law, while the gravitational force was then added to the magnetic force to calculate the total net force. Net force was then used to update the position and velocity of the magnet over time. The results of the computational model yielded a graph that showed a high initial velocity downward. This was consistent with the magnet falling through space before entering the tube. Then, when the magnet entered the tube, the velocity decreased and held steady as the magnet fell through the tube. Finally, the velocity increased again when the magnet fell out of the tube. The computational model also calculated the time spent in the tube to be 4.596 seconds. When we look at the results of the computational model, we see that the blue color indicates a current that flows in the counterclockwise direction. This can be confirmed using the right-hand rule. However, if the magnet was flipped around, the current would flow in the opposite direction, or in the clockwise direction, and would yield a red result. When we compare the results of the computational and experimental models, there is a 77.87% difference. This difference most likely results from magnetic field interference from household devices, as well as timing errors in the experimental model. When we look at the graph from the computational model, we can see that the magnetic force acts in the opposite direction as gravitational force, or in the positive y direction. We know this because the magnet slows down when it enters the tube. However, we also know that the gravitational force still has a larger magnitude, since the magnet continues to fall in the negative y direction. If the resistivity of the conductor were essentially zero, the current would increase, because EMF is equal to I times R. This would in turn yield a greater magnetic force, which would in turn cause the time the magnet spent in the tube to increase. On the flip side, if holes or slots were cut into the tube, the current would decrease. This would yield a lesser magnetic force, which would then cause the time the magnet spent in the tube to decrease. In conclusion, in this lab, the time it takes for a magnet to fall through an aluminum tube was experimentally determined. Then, that same system was simulated computationally, and the time was calculated using the simulation. Finally, the results from the computational and experimental models were compared.